thank the organizers for putting together such a great conference. And okay, so with the introduction, let me start. So I'm going to talk about a joint work with Charlie Pfefferman and Garving Lully on interpolation of data in Sobolev spaces. And I think you've probably seen some of the problem set up before in Charlie's first lecture. But here's the plan for my talk. So I'm going to review what the problem is at first, and then I'll give you an outline for what I plan to do. So the Whitney problem, so this is not the classical version that Whitney solved in 1934, is stated at first for the space of smooth functions Cm of Rn. And this is equipped with a norm which measures how small the derivatives, or how large the derivatives of a function can be. And this is the norm on Cm of Rn. And the Whitney problem asks, well, two questions at first, and then there's been interesting work on a third question done recently in the past 5 years. But the Whitney problem asks, let's say that we're given a closed subset of Rn and we're given a function on that set, an arbitrary function. What conditions must we place on this function in order for there to exist a function f, capital F, with a prescribed smoothness belonging to this space that matches little f on E? And secondly, assume that such an extension exists, then how small can we take the norm of the extension? And that's a more quantitative problem, whereas the first question is qualitative. And then interesting work has been done in the past 5 years by Pfefferman and Klartag. If you have a finite set now, are there efficient algorithms to compute a near-optimal extension and to estimate the near-optimal norm? This is the Whitney problem in its classical setup. And so most of the focus of this talk will be to shed some light on how one can hope to replace this space of smooth functions, Cm of Rn, by another space of smooth functions, by the Sobolev space. And we hope to prove similar theorems to what was done in the past decade for Cm of Rn in this new setting. However, there will be differences, and there are differences in the new setting, and we'll need to take those differences into account. So I hope to provide some sort of proof at the end. But first I'll state the problem again, more carefully define the Sobolev spaces, give some history, and give some examples for what has been done in the past, very specific examples. And then I'll state the main theorems and discuss them a little bit. And then I hope to at least talk about the proof. And the proof that I'm going to give is very closely related to the last lecture that Charlie talked about on the classical Whitney extension operator. Okay, so what are the Sobolev spaces? So we're going to fix integers m and n greater than or equal to 1 and fix some real number. And I'll put the restriction down p is more than n. Then the Sobolev space is the space of functions on Rn whose mth order derivatives are in LP. And I'm going to put a semi-norm on the space by taking the sum of all the LP norms of all the mth order derivatives. And notice that polynomials of degree m minus 1 have semi-norm 0, so this is not a norm. The second piece of notation you have probably seen on the last 4 sets of slides is the jet of a function. So the jet of a function at a point x is just the m minus first order Taylor polynomial, and there's the formula for it. Okay, and so the only main technical tool that I will use, and I will not even really use it until the very end, is the Sobolev embedding theorem. So it states that because p is more than n, and this is the reason we make the restriction, every function can be modified on a set of measures 0 so that it is a Cm minus 1 function. And its jets satisfy certain estimates that are usually called the Sobolev inequality. This is the Sobolev inequality. So it's just Taylor's theorem in conjunction with the fact that you have embedding into Cm minus 1, and you actually get a Holder exponent alpha, which is 1 minus n over p. But in particular, any function in LMP of Rn is continuous. Okay, it's more than continuous. But in particular, it's continuous, and so we can formulate the Whitney problem for finite sets even. Okay. All right, now the Whitney problem can be posed in any function space X, but we're going to consider two settings, as long as you have embedding into continuous functions. But we'll focus on these two settings in this talk. So either the classical setting or the new setting. So what does the Whitney extension problem say? So this is almost a repeat. But again, given a arbitrary subset of Rn and a function on that set, qualitative question, does there exist an extension in this prescribed smoothness class? If so, now the second problem is, can we take it to depend by a simple way on the data? So is there a formula or an extension operator that takes the data f and produces a capital F in a linear way? And similarly, we can ask about computing the smallest possible norm and computing a near optimal extension. And we'll talk about this in a moment. So let me clarify those slides with some definitions. So the trace space is the set of all functions that can qualitatively be extended. Okay? So x of e is the set of little f so that there exists an extension. This is defined for an arbitrary set E. The semi-norm measures quantitatively how well of a job we can do extending the function. Okay? It's the norm of the best possible extension of the data. Okay, so what are we looking for? That's the next slide. There we go. Okay, oh, I have this thing too. Okay, so we're looking for, first of all, a C-optimal extension. Okay, so what is a C-optimal extension? It's a function that matches the data on E and which has nearly optimal norm to within a factor of C. So recall that the trace norm is the optimal norm. And we're also interested in understanding this near optimal norm, so we want a formula that approximates this optimal norm to within a factor of C and 1 over C. If we can do these two things, then we'll say that we have solved the Whitney problem. So characterizing by a linear method how to compute C-optimal extensions and how to approximate the trace norm. And here I'm going to show you some examples of explicit formulas in various settings. Okay, so some remarks on C. So C could have been any number there, but a 1 optimal extension, the best possible extension, the one with minimal norm, may not exist. And even if it does exist, it could be very difficult to find. And I'll mention one situation, Charlie mentioned one situation already, where somebody found a characterization of the least possible norm in a very special case. But this is a very difficult problem. Okay, a problem which is almost equally challenging is the problem of characterizing C-optimal extensions for even reasonable values of C. So that's not going to be our setting. So our setting will be that the constant C is allowed to depend on Mn and P, and in a very nasty way. So that's some bad news, but that exists in a lot of the work in this field. Okay, so from now on, constants depend on N, or arbitrary constants depend on Mn and P. Okay, so what is the history of what has been done so far? So, sort of before Whitney, did his work in the 30s, well, there was no Whitney problem before then. After Whitney did his work, there was, I'm missing some history here, but the result I want to really point out is the result of Brudny and Schwarzman, which handles the space C11 of Rn. So these are functions whose gradients are Lipschitz. This is analogous to C2 of Rn. In fact, for finite sets, it's just the same problem, minimizing the C2 norm. And then Pfefferman's work solved the problem in full generality for Cm of Rn, and both of these results were based on finiteness principles. So I'll give some examples of what those look like in a moment. Okay, now motivated by the finiteness principle and the proof of Pfefferman's result on Cm of Rn came the work of Pfefferman-Klartag, and analyzing the proof, they were able to pull out an efficient algorithm using ideas from computer science, such as the well-separated pairs decomposition. Okay, and then, so there was some work on C-optimal extensions where you can take C to be 1 plus epsilon, but this problem is, there's still interesting problems here that are unsolved. And then actually in a specific case, there's an explicit formula for the smallest possible norm, which is somewhat interesting. but you have to take a very special C11 norm using the difference of the Euclidean norm of the gradients. You can't use the LP norm of the gradients, I don't think. Okay, so these were all for Cm of Rn, and then the problem was sort of broken open in 2010 when Schwarzman showed that the classical Whitney extension operator, so the very same method that if you were in the last talk you saw, that very same method also produces an optimal function in the Sobolev space LMP of Rn. Okay, so it's optimal in a wider class of spaces than just the optimality that Charlie showed you the proof of. Of course, the conditions on how to compute the norm of a Whitney field in the space LMP of Rn are different conditions. They're not just the simple ones from Taylor's theorem. But still, it gives you the optimal extension. The extension operator gives you the optimal extension. Okay, and then, so in my thesis, and then I'll mention actually the result of Schwarzman, L2P of R2. So now you're given function values only on a set, but you're asking to minimize the LP norm of the Hessian when P is more than 2. And this is a hard problem because there's more pointwise information that could be specified. Potentially, the function's gradient makes sense everywhere. And you better, if you're trying to keep the Hessian small, you better make sure that the gradients of the function aren't changing too much. You have to pay attention to the gradient, but the gradient isn't specified as data. You're just given function values. That's why it's harder. So let me go back to the finiteness principles, since they'll motivate the statements of the main theorems in general. So the first finiteness principle is that of a finiteness principle for the space of Lipschitz functions on Rn. The space with the least amount of smoothness turns out to be the easiest. So if you're given let's just, for now on, restrict attention to finite sets, since I'll be speaking about quantitative problems. Given a finite set of points and a function on that set, the problem is to minimize the Lipschitz norm of any of an extension of the function. Okay, there's a simple formula for the minimal Lipschitz norm. It is just the restricted Lipschitz norm of the function little f. Why? Because this is clearly less than or equal to this, providing a lower bound on the minimal Lipschitz norm, just by restricting the sup to x and y and e. Moreover, if you have a function where this quantity is, let's say, 1, then you can explicitly write down an extension, capital F, defined on all of Rn, whose Lipschitz norm is at most 1. Roughly, the way you do it is you take a cone, the graph of a function whose graph is a cone, that is x minus y for fixed y, and you take one centered at every point of e, for every y, and you translate the cone up so that it sits right on top of the function value, and then you take an inf over all possible cones. So this is the higher dimensional analog, a higher dimensional analog of the natural thing to do in one dimension is just to take a piecewise linear function that interpolates the data. Okay, so we have an exact formula. And now I want to point out, I'm just going to go through something very quickly now because it came before in Charlie's lecture. This is very expensive to compute because you need to examine all possible pairs x and y and e, and there are n squared such pairs, order n squared. Okay, so if we want to ask for formulas that can be computed efficiently, maybe that's our criteria for a finiteness principle or for something simple, we can be saved by some ideas from CS that Charlie spoke about. Up to constant factors, this quantity, which is order n squared to compute, is approximately this quantity, which is order n to compute. One only needs to look at pairs of points x and y that come from a set of pairs whose size is at most a constant times n. This is the well-separated pairs decomposition. That's where the points come from. And because of work in computer science, the well-separated pairs decomposition can be computed quickly. And so one can generate this formula quickly. And in fact, these points don't depend on f, but only depend on e. So let's summarize what we've seen. Putting the two things together, the minimal Lipschitz norm is approximately the smallest possible, is approximately given by this formula. And this formula can be computed in time O of n. For each new f you get, you can compute this quantity in time O of n. See, that's optimal, because it takes order of n operations just to read the data. Okay. Okay, so now for something that's much less trivial, a two-dimensional problem. Okay, so let's think about minimizing the C11 norm. So this is the definition that I use for the C11 norm of a function subject to pointwise constraints. Now, this is a very hard problem because we're not in the realm of classical Whitney anymore. We're given function values, but we need to know something about gradients. Okay, so the only point of this slide is there's a very simple explicit criteria, and it's very explicit. What is it? So let's just assume the set is in general position. Okay? Then the minimal norm is this. It is computed by taking a soup over 6-point subsets, Z1 and Z2, where Z1 and Z2 are two different triangles contained in E. And what's the discrete analog of the Hessian for a function defined in an arbitrary subset of the plane? It is pick 3 points here and 3 points here, and take the unique affine polynomial interpolating the data here and subtract the unique affine polynomial interpolating the data here, and then divide by something like the distance between the two triangles. That's kind of like the Hessian if you were thinking about difference quotients. Okay, and so this theorem provides a very simple formula which has some, it's intuitively plausible in some sort of sense. And the key is actually that this only depends on 6 points at a time. That's optimal. There's no formula like this with 5 points here, everywhere. Okay, so one actually might think that in R3, by the same geometric intuition, you should be using 8-point subsets, but it's not true. So actually, for C11 of R3, you need, for a formula like this, you need to look at function values on 12 points at a time. And then some sort of linear combination one can form that gives you a nice formula, but it's 12 points. All right, anyway, so never mind that. But the point is that these results have been generalized to the setting of Sobolev spaces. So these first two are the generalizations. And then further work, and this is the joint work with Charlie and Kevin, comes down to extends this work to all Sobolev spaces. Okay, so I wanted to give you some explicit formulas before I state the main theorems. So let me show you the theorems of Schwarzman. Okay, they are simply that if you want to minimize the L1p norm of a function on a finite set, one simply takes the little lp norm of divided difference quotients, fx minus fy, instead of before we were doing the Lipschitz norm and we had a max here, and now we just take the sum. That is a simple formula which describes the L1p norm. And moreover, it can be efficiently computed because of this property that the geometric constants here vanish except for O of n pairs. And the same theorem is true for E contained in R2 when you're looking at the L2p norm. Okay? So in the same setting as the previous theorem, you take all pairs of triangles and take the difference of the gradients of affine interpolating polynomials, and that's the L2p norm. Okay, so this is what I mean by explicit formulas. And now let's see something that looks less explicit. And I just wanted to say that actually in the proofs of these theorems, one actually constructs the optimal extension. I mean, that's what you would expect. If you're proving that this thing is, let's see, bounds below the L1p norm, you better compute an extension somehow. That's if it's constructive, the proof. You're going to compute an extension whose norm is less than or equal to that. Okay, so naturally these proofs are constructive, and so you compute extension operators. All right, so now the results for arbitrary Sobolev spaces, and these look less explicit, and I'll comment a little bit on what these formulas actually look like. The first theorem is, now we're in the set of arbitrary sets. So for an arbitrary subset of Rn, there is a linear extension operator, which produces an extension T of f of the data little f, and Tf is within a factor of C1 of optimal. Okay, theorem 5 is that the trace norm is given by an explicit formula, and That is, there exist linear functionals such that the trace norm is approximately the little LP norm of the linear functionals psi L. This looks just like the formula I had written down before for the two cases L2P and L1P. Moreover, there aren't too many linear functionals present. This is analogous to the theorem about Lipschitz functions, that one can compute the Lipschitz norm using a sup, a max, over at most O of n pairs. That's the analog. And we can say even more, and that will be the next slide. Now, these constants are reasonable and unreasonable. The number of functionals is reasonable, but the quality of the formulas is unreasonable. So that's the 10 to the 10 to the 10 to the m, or m times n. But this is something like 10 to the n. This is for, yes, so for all m and n greater than or equal to 1. Okay, so now what can we say about the structure? And this bodes well for algorithmic work. The point is that one can, okay, let me go back one slide. So this formula, the question is, can you write it down on a computer using space order of n? That would be the optimal formula one could hope for, order O of n. And the claim is that, yes, one can write these functionals down on a computer. So I'm stating a theorem that has no meaning because I didn't define this notion of assisted bounded depth. But there's a special structure that these objects have. And a corollary of this structure is that you can write them down on a computer. And notice that there are at most n functionals. What's one way that this might be possible? One way is that each functional only depends on 6 or 10 or 12 function values. It's like a little weighted average. That's one thing one might expect, but we don't prove that. But we still prove that we can write it down. So let's see an example. Just two quick examples. Functions with bounded depth you've seen already. Here are some that look like difference quotients, divided difference quotients. So each of these depends on only 3 function values. Okay, we don't produce these. We produce things that look like these. So this is a motivation for assisted bounded depth. For instance, say you have a set of points and a function little f. Say you partition E this into k disjoint subsets. And then you define a weighted average, which is given by a sum of function values on each of these subsets times some arbitrary weights supported on the subset. Okay, so this is a mean, and this mean is allowed to be over a very large portion of the data. Maybe the data is 10 to the 10 to the 10 points, and here I'm taking half of the points on the left side of the Rn, and I'm taking the average value over the whole half. Okay, now, the linear functionals that we construct look like formulas like this, where we're just taking selecting a few of these large means, and subtracting them or adding them in various ways. Now, it's clear that one can represent this on a computer in space O of n, because one can write down all of these weights for x and ek in space O of n. And after one has those weights, this is a simpler representation that takes constant space for each of the functionals. So that's what we produce. And let me remark, it's a conjecture. It's a conjecture whether you can take these x's that depend only on a constant number of points. It's a conjecture that you can, sorry. But it's not known. It's known for L2P by the theorem of Schwarzman I quoted. Okay. So what are some ideas in the proof? And let's see, I was betting this would take 25 minutes. Okay, good. Wait, did it? When did I start? Okay. All right. So some ideas in the proof that will take the remaining part of the lecture. And I won't prove the theorems in full generality, but I'll give a setting where the main ideas come through. And in reality, the main idea that I'll mention at the end is responsible for several things. It's responsible actually for the whole proof of this theorem. But that main idea, when you apply it to the general case and mix it with some of the stuff Charlie's talking about in the next couple days, gives you the general proof. So I'll highlight what the main idea is at the very end. Okay, so this is our simple setting. We're going to do L1P of Rn. So we're minimizing the LP norm of the gradient subject to constraints. And the theorem of Schwarzman says that one should just use the classical Whitney extension operator, which you have just seen. So I'm going to talk about the proof of this and what needs to be adapted to the setting of how to adapt the proof of the classical Whitney extension operator to the setting of Sobolev spaces. And it'll follow different notation from the original proof of this theorem by Schwarzman. Okay, so what are the main things? So the main things in defining the Whitney extension operator is forming a decomposition of a large cube that contains your closed set E or your finite set E, forming a decomposition of a large cube into a bunch of small cubes. So we'll do that. You've seen how to construct a partition of unity. I'll review what the properties are. And then I'll talk about the different part, which is how do we assign points of E to cubes. And I'll define the extension, and then we'll talk about the proof of proving optimality. Okay, so let's start the proof. So I'm going to assume that E is finite and that cardinality of E is more than 2. And I'm going to fix a large cube that contains my data inside the middle 1/10. That's just like how we started before. And okay, so now I'm going to use a different word. I'm going to do a Calderon-Zygmunt decomposition, but a la Whitney. This is just a Whitney decomposition, but the unfortunate fact of Whitney decompositions is that they contain an infinite number of cubes. Okay, so I would rather not deal with infinite partitions. I'll do the analog where it's a finite partition, but the picture will be the same. In particular, these 4 properties are satisfied, which look familiar. So the cubes cube form a partition of the unit cube, a finite partition, and you still have this property called good geometry, which is whenever 2 cubes neighbor each other, then their side lengths differ by at most a half, or just a factor of 2, or a half. And this is the different one. Before, we were saying that E intersect 3Q should be empty. Now I'm going to stipulate that I want E intersect 3Q to contain 1 point, but E intersect 9Q to contain at least 2 points. This, it turns out, is just what happens if you take the Whitney decomposition and you cut off length scales that are too small, okay, that are like below the nearest neighbor distance. Okay, so what does this thing look like? It looks something like this. You saw this picture before. And these cubes are small here because there are some points of E nearby. And when we did our cutting rule, we were cutting according to a stopping rule that said stop cutting when something happens. Let's see what the stopping rule is. So there are a few points of E here and a few points of E here. But what's the stopping rule? How do you build the thing I just spoke about? Again, it's the same thing. And I'm going to go through this quickly because it's not very different from what Charlie spoke about. You cut a cube up into pieces based on whether or not a stopping rule occurs. In this case, we just make the stopping rule the thing that we want satisfied by CZ cubes. We want E intersect 3Q to contain 1 point. Okay, so that's our stopping rule. All right, so we first cut Q0 into a bunch of cubes, 2 to the n dyadic subcubes that are its children. And these are the stage 1 cubes. And for each stage 1 cube, we check whether the stopping rule is satisfied. So for each of these cubes of side length 1/2 of the large cube, each of these stage 1 cubes, we check to see if E intersect 3Q contains 1 point. If it does, then we keep the cube and we throw it in our bag.
At most 1?
At most 1. At most 1 point. If E intersect 3Q contains at most 1 point, we put it in our bag. If E intersect 3Q contains 2 or more points, we're going to have to keep bisecting it in order to get the good property that we want, which is E intersect 3Q should contain at most 1 point for every cube that we generate. Okay, so that's stage 1 cubes, and we keep bisecting if this occurs. Okay, so you go on, da, 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 da. As long as you have cubes that are not in your bag, so as long as the thing doesn't partition the unit cube, let's say that we have a stage K cube. Its side length will be 2 to the minus k times the side length of the big cube. Again, we check to see whether the intersection of E with 3Q is less than or equal to 1 or more than 2, greater than or equal to 2. And if this happens, we keep QK, and we continue on forever. Why must we stop? Well, we must stop because if you have any cube in your decomposition which has side length less than or equal to the nearest neighbor distance between 2 points, or 100th of that, then that cube will automatically satisfy this condition. So this process eventually stops. And now that we have all the cubes in our bag partition the unit cube, or the big cube, Q0, that's our CZ decomposition. And so here's a picture. So these were supposed to be the points that generated the picture I showed you before. Here I don't cut this cube because 3Q is right here. Doesn't contain any points of E, but I do cut this cube because 3Q, it turns out, contains, there's 6 points there. So I'll cut this into a bunch of pieces, but I'll put this in the bag. All right, so now what do? So again, we have a decomposition of the unit cube with good geometry. So it satisfies these properties. You can construct a partition of unity adapted to that decomposition. So there are a set of smooth functions that look like little bump functions supported on Q. There may be one in the middle half of Q, and they vanish outside of 1.01 Q. And the derivatives satisfy the natural estimates for bump functions adapted to small cubes with side length delta Q. They satisfy this bound. And the cubes, the sum of these functions equals 1 on Q0. Okay, so that's the setup of the classical Whitney extension operator. And now you try to choose information about the extension locally on each cube in your decomposition in a clever way, hopefully, so that at the end of the day, by patching together the local extension with this partition of unity, you generate an extension of the whole function, little f. The way Whitney does this is as follows. He takes, so now we're working with just function values, right? So this is classical Whitney extension, but you're doing zero jets, 0-degree polynomials. Okay? That's what makes sense for this problem. So we're just going to follow that. So Whitney says, pick a cube for each cube Q, find essentially the closest point in E. We know that this distance is proportional to the side length of Q. This still holds. In the pictures that I drew, it holds. So now that we have a point that's at most, so what is this point? This is just the point that's in 3Q intersect E, right? Or one of the points in 3Q intersect E. Now this point is very close to the cube Q. And Whitney says, you should just look at the function value there and choose that function value to be your local extension on Q. And now patch together with a partition of unity in order to smooth out the edges. Now, so the question is, in this proof, what am I going to do? Am I going to choose just any point? And this is where the difference occurs. I'm not going to choose just any point in 3Q intersect E. So in this proof, which one am I going to use? So I'm going to look at, I'm going to pick a point xq that's nearby to E. So it's still one of the essentially closest, but there are a lot of options. So I'm not just going to choose any point. Okay. So I just wanted to warn you about that. So how do we choose points? Okay, so let's first make a couple of definitions. So I'm going to define an important cube. Okay, so an important cube is a cube Q so that 1.01 Q contains a point of E. So what do important cubes look like? Important cubes are the cubes that intersect E. These didn't arise before because we were doing Whitney decompositions, but now they arise because we're doing finite decompositions. So this cube is important, but these two cubes aren't important. Now, important cubes are cubes where it is immediately obvious how to extend the function on that cube. Because I'm given a function value at a point, like in the center or somewhere inside the cube. So I should clearly just take the constant function there, until I have to perhaps transition to another constant function over here by our partition of unity. But still, it's clear that I should be using the function values of E, of the single point, on these important cubes. However, for the not important cubes, there are 5 function values here nearby. Which one do I choose? Again, that's the problem. Okay, but we're going to use function values on important cubes to specify function values on not important cubes. And my goal is to describe that. Okay, so first of all, this is the main point, and the construction of the assignment is actually based on the construction of something else called an exponentially decreasing path. And these can be formulated just in any decomposition of a unit cube into a bunch of subcubes that satisfy good geometry and et cetera, et cetera. There's really something very global about this, and in the proof for LMP of Rn, we use the same paths. That's why I wanted to introduce it in this simple setting. Okay, so how are we going to choose points via paths? Okay, first of all, what is a path? So an exponentially decreasing path. It has a starting point and a terminal point. Rather, a starting cube and a terminal cube. The starting cube is the cube Q from which we're starting. That's Q0. And Q is given to us here. And given Q, we build a path. The path satisfies that the last cube in the path is important. That is, it contains a lot of information. All right, so my pointer's sharp. Oh, there it goes. Ah. Okay, what else happens? In the path, two neighboring cubes touch each other. And lastly, the side lengths of the cubes are decreasing exponentially. So the side length of the kth cube is bounded by some factor less than 1 to the power of k minus l times the side length of the lth cube. So these are getting smaller as we move forward. And finally, let me just state the obvious. If the cube Q is already important, I'm not going to make a path. So if Q is already important, there's no path. It's just the singleton path, which satisfies those properties, of course. This is what paths look like. So here we have a CZ decomposition, and it has two important cubes. There are 2 points of E here. I can't really see them, but they're there. And starting at this cube Q, I'm going to find a path that's exponentially decreasing to a little cube that contains a point of E. Now, the information is going to spread up. So there's data point here with a specified function value. I'm going to use that function value on this cube. That's how paths are used to find points. Okay, so actually, before I get to that, how do we construct paths? It's actually pretty nice. So it's just gradient descent. It's like gradient descent on decompositions of cubes. Okay, we go in the direction of smaller cubes, and eventually we have to reach a cube of minimal side length. And the reason that cube had minimal side length was because it contained a point of E, and therefore was important. Okay, so the one thing I'll prove will be this construction of paths, and unfortunately this will be careless, and I won't be able to show you the careful construction that we need. But I'll show you the statement of the careful construction, or the properties, the extra property it satisfies. Okay, but now we're just focused on finding these paths. Okay, so here's the cases. So if Q is important, then we were supposed to just have a path of length 1. Okay, so I do that. Okay, now let's go on to the non-trivial case, if Q is not important. So if Q is not important, I'm going to look in my nearby neighborhood, okay, 9Q. So I'm going to blow up by a factor of 9. Okay, and now I'm going to recall a property that we had before, 9Q intersect E is not empty. Okay, but we're doing gradient descent, or the analog, so we blow up by a factor of 9, look in our neighborhood, our immediate vicinity. And the subcase, the first one, is that every cube in our immediate vicinity has side length larger than that of Q. Then what do we do? Well, pick any of the cubes Q in this Q prime that intersect 9Q, and notice that there are a bounded number of them, because the Q primes have side length at least Q. So you can see that there are a bounded number of such ones. So therefore, we can connect Q with Q prime by a path of bounded length. So we have 9Q tiled by cubes of side length that are at least as large as that of Q. We can go from Q to that Q prime with a path of bounded length. That's easy, but I'm going to go to the cube Q prime that intersects E. Remember that 9Q had at least one point of E in it. So there is one of the Q primes that contains a point of E. I'll go to that one. That Q prime, by definition, is important. Okay? So that's how you construct it in this case. Okay, so now that's the easy case. That's like the case where we're almost near the local minimum in gradient descent. We just have to go a little bit. What if we're very far away from the local minimum? Then there's a recursion procedure. So how does this work? So suppose that the cube is not important as before, and we're still going to look at 9q. But now there is a cube in that intersects 9q whose side length is 1/2 or less that of delta q, that of the cube q. So there's a strictly smaller cube in our immediate vicinity. Then I pick the one which is closest to q in the Euclidean distance sense. Okay? Now, if you think about it a little bit, we can connect this q with that q prime by a path of bounded length because of the assumption that this q prime is closest. Okay, so here's that connection, q to q prime by a path of bounded length. Now I look at q prime. Q prime has half the side length or less of q. So let me recurse. I'm going to build an exponentially decreasing path from q prime. It satisfies all of the properties I stated before. It's exponentially decreasing, and it ends in an important cube, and it starts at q prime. Now you concatenate the two paths. So we go from q to q prime using 10 to the n cubes, and then we go from q prime down to q sub l prime. So this is segmented. If you look at it, what it is doing when it's recursing, this is segmented into blocks of length 10 to the n. And each time you hop 10 to the n over, you go down by a factor of a half. And so this is exponentially decreasing in the sense that I stated. Okay, so these are the properties. And now I claim that I need something else in order to prove the sharp version of the theorem that I stated. So here is the important point. In addition to these properties, I can choose paths in such a way that the number of cubes q and q prime which touch, however, they have a different terminal cube, is bounded by a constant times n. Let's see a picture to describe this. So these are the two paths. We're going to different points of E. And this is one such pair, q and q prime, which lead to a different point of E. And I claim that the number of such pairs is at most a constant times n. And then I furthermore claim that that's important. Now, this construction is different. I can't just do the simple thing I did before and expect to have this property. Because I was treating each path as its own object. I wasn't studying how paths relate to each other. But there is a more detailed construction which gives this good property that I mentioned before. Okay, and we'll use that. But I won't talk about the proof. Okay, so now how do we assign by paths? So let me go back. Remember that at this cube there's a point of E. So I'm going to assign to this cube that point of E, the point at the end of the path. So first find the path, and then pick the point xq, which is inside 1.01 times the terminal cube and inside E. That's the assignment. Okay, so now how do we define the extension? We define the extension a la Whitney. And then how do we prove good properties of this extension? We'll get to that later. But we learn the function value at the, we just set for this choice of xq, assignment map, and for the good partition of unity introduced before, we use the constant function f of xq as our local extension on this big cube. And then we patch together with a partition of unity. This is exactly Whitney's construction with the additional fact that we're using paths. Therefore, the Lipschitz norm of this function is bounded by the optimal Lipschitz norm because of Charlie's proof for zero jets. But we're using CZ decompositions instead of Whitney decompositions, but that's not really important. Okay, so first thing. So this is not the crew of the matter, but it needs to be checked. And maybe if I forfeit, how much time do I have? Okay, so this function is an extension. That's obvious. And this is the proof. It's not long. Okay. How do you estimate the norm? This is, okay, so I decided to include the ugly details that Charlie didn't want to include. Oh, wait, no, Charlie did this. Okay. But it's more messy for Sobolev spaces. But you do the same trick. So,
You could see it.
what's that?
But you can see it.
You can see it. Ah, all right. You can see it. Okay. Okay, so we fix a point in Q prime, where Q prime is some CZ cube, and we do Whitney's trick. We can't expect to estimate the gradient of this function just by applying the gradient to it and then using boundedness of the gradient of theta q, because these length scales are huge. The gradient's huge when the length scale is small. But we do the Whitney trick. So we compare, we subtract and add a single function value, f of x q prime, and we just take the gradient. And that actually cancels out that thing. So there are less estimates in this version. This goes away when you take the gradient, and you have just that term. And you don't even have the Leibniz rule. So that's good. These are just numbers. Now you integrate. That's the difference. And when you integrate the Pth powers, because this sum is bounded, it only contains a few terms by the good geometry. Maybe at most 100 terms in the sum are non-zero. You can just bring the Pth powers inside, and you get this formula for the integral over q prime. Okay? Now you sum this formula. And I'll be stopping soon. But maybe the computer knows that I'm late. Okay. So we sum this formula over all q prime, and here's what we get. So the LP norm to the Pth power is bounded by the sum of all discrepancies of the function values on neighboring cubes. And the main point is, this is just a computation, it's ugly, and the real point is that the sum end is non-zero for all but c of n, c times n, distinct pairs of cubes. That's by the extra property when we did the careful construction. I didn't show you that. So this, if this function is optimal, it has the right norm with the right formula for it. Okay, now you can trivially extend this function to all of Rn. It was only defined on Q0. That's not a problem to extend it to all of Rn, satisfying the same properties. You don't ruin the norm. But obviously the most technical part of the proof, which has to be here somewhere, is that you need to show that this is optimal. This is easy in the previous case because you just use Taylor's theorem. You have a max of differences. And by Taylor's theorem, this is bounded by the L infinity norm of the gradient. If this were a max instead of a sup, a sum. But this is the hard part for Sobolev spaces, and so in this proof, we use paths. To prove this thing, we use the careful construction. We don't use the careful construction. We just use the fact that there are paths that exist, and that's how we got the points. And so then the final remark is that this proposition implies the theorem. Okay? For any g in L1p of Rn, we have this inequality. That implies the theorem. So we have this upper bound on the norm of the thing we construct, but it's less than or equal to g whenever g equals f on e. And I think I'm definitely out of time, and I'm running late, so I'll stop now. But it's not so easy to prove. It's more difficult than the L infinity setting.